So the whole idea is the textual. This is called the BridgeTower. It came out from Intel, where my
Uh-huh.
dad used to work, and they have an AI division. And they developed this thing called the BridgeTower,
Okay.
and it's supposed to be like this, two towers, right? This is the text encoder. This is the visual
Uh-huh.
encoder. So it's able to take images. If you're able to take images, then you can take videos because videos, right? You probably heard about frames per second, like 30 frames per
Mm-hmm.
second, 60 frames per second. That pretty much means how many images are produced per second. So when you're lagging, right, when you see a video and your YouTube is starting to lag,
Like,
that means
yeah.
that your frames per second has reduced to like 5 or 10, and then you can see like it's just very choppy and it's just jumping very, right? So
Yeah.
essentially, that's what it means. So it's visual. So that's why I'm trying to make a point that it's not a image encoder. It's visual. So you can take in visual data, and hence you could probably take in videos as well, because it's just more images. That's it at a time.
Okay. Yeah.
So these are the two towers. You feed the data in there. They do a whole bunch of block, really AI stuff, and then it feeds into what this is called a cross encoder. So essentially, it processes the data and encodes it and fuses the data of the text and the images or video, fuses them
Mm-hmm.
together, puts them, you making a smoothie, and then together,
Yeah.
you know, you push it out, and then it creates these embeddings. So that's what I'm working with. This is the model that I'm using, and it's called BridgeTower. There you go. So your multi-embedding model exploration. So in the beginning, to look at it, it's here is just like you see a motorcycle, all these things. And so what if you look at here, if I look at these, it's just a motorcycle, another
Mm-hmm.
motorcycle, or a pillow, right?
Mm-hmm.
So
Mm-hmm.
you have those, right?
Mm-hmm.
Downloaded them. I look at them, but oh, it's here. Oh, I didn't realize it. There it is. See, and then it comes the text. So it's an image text pair, like a pair of shoes. So here's my
Yeah.
pair of shoes here.
And you didn't write that like that. The computer wrote that. The bottom text.
This one? No, no, no. It
Mm-hmm.
came. It came with it. No, no, no. Caption here. White pillow on
Oh.
a bed laying. Yeah, I just wrote it because it was just three data points. So I was like, I can write that. It's fine. So I
Okay.
put that right. Here's my pillow that I just showed you. It's a different size of an image, and then I'm computing. Right? I'm gonna be computing them then. Here's the bridge tower. You see the bridge tower here?
Mm-hmm.
Yeah, this is the model that I'm using. So I'm using it. So it's a processor, and for that. So this bridge tower processor constructs a bridge tower processor with Rhapsody Roberta tokenizer. So this is probably used for the. I don't even know what's the difference between processor. I need to do more research on that bridge processor and bridge model. I think this one is made for the text or creating the inputs encoding, and then the model. I think there's two steps to it with this thing because I'm doing. The first step is, yeah, I'm creating the encodings with the processor, and then the encodings are transformed into the model. So then the model is creating, yeah, okay, there you go. So then here's the model. You can print it out. This is the model. All that thing that I showed you, all these little towers. This is kind of how it shows you. This is kind of like what do they call it? They call it a dictionary or like a state dict, which describes like a guy like an AI engineer will be able to look at this and say, okay, this layer has 768, nodes, and then it's times 12 or whatever something. It's still kind of I don't really understand it so well. This is a completely different kind of thing. Has a normalization layer, has a linear layer, normalization layer, linear layer, whatnot. It's too much. Um, this is where we create the embeddings. So we create our encodings here. Then we move our encodings to a GPU, right, for more hardware optimization there. So it runs in parallel all these things, so it's faster. You get your answer faster. And then from there, the encodings, I feed it into the model, and it creates these outputs, and these outputs creates these vectors. This is the vectors here, this tensor. So this is the text feature, and this is the pooler output. So this is essentially all of the vectors together here. So that's what you're looking at here. So now it's like, okay, here's the first embedding. So that's for the first image and the image text pair. And so
Yes.
that's what it is. So that's like the motorcycle. As you can see, the length of it is 1,536, meaning that's how many vectors that. This is one vector, two vector, 3D, and then so on.
Mm.
I vertically stack it so then I can put them all together. And so at the end of it, I have, I don't know, I still printed out the first one. I'm supposed to have three of them together at that point when I vertically stack them. This is just some coding. Then I do an L2 normalization. So an L2 normalization, it's important when you want to do a thing called similarity measures. So
Mhm.
right, what I talked about how when things are positioned close together, if the topic is, if you have two images, right? I had two motorcycles
Yeah.
and then I had one pillow. So these two motorcycles are very similar to each other, right? Based on the caption and
Mhm.
in the context of the image. But a pillow is
Yeah.
completely different, and also the text is different. So the problem is though, when those vectors are created, they are unscaled or unnormalized, meaning
Mhm.
that the magnitude, these numbers that you're seeing here, like this, what I'm highlighting here,
Yeah.
these numbers could be very large in scale sometimes.
Mhm.
And what you want to do, why you want to normalize is that when you normalize it, meaning that you force all the vectors to be a value from 0 to 1. That's the idea. From, you know, or from or like a specified range. So it could be from -1 to 1 or 0 to 1.
Mhm.
And because it allows it to, when a machine learning is learning on the data, it allows it to converge on an output a lot faster because the distances are kind of normalized in a way. It doesn't allow for the machine learning when it's training to fall into a local optimum solution space. I'm
Mm.
using a lot of jargon. So what I mean by that,
No, but mhm.
imagine you have this piece of paper here
Yeah.
and you have a lot of these little
The little
hills,
waves.
little
Okay. Yeah.
like a hill.
Mhm.
Some of these, when you have it like this, let's say the optimal solution is at the bottom of this.
Mhm.
But sometimes, because there's many little waves in there, you can end up in a optimal, like a little hill, but
Mhm.
it's not as deep. It's a little more shallow. So it doesn't
Okay.
perform as well. That's the
Mhm.
idea.
I
So
see.
it helps with that. It helps with the training because it makes it easier for the machine learning to see, oh, this is very different from this one. It doesn't have this outlier all the way out there, and then it makes the machine learning freak out. That's kind of like I'm trying to explain it. Might explain it right. So here I do the similarity computing. So this is what I'm calling here is a cosine. Cosine. You probably learned that in math. Sine waves and cosine.
Mhm.
That's probably
Calculus.
what you learn in polar coordinates, right? You remember that with the theta, the angles?
Mhm.
Right?
I
So
think
imagine
so.
your polar coordinates. In this sense, it is trying to see if two separate objects are similar to each other based on the angle. So if they're more similar to each other, the angle is closer to each other. If they're more opposite of a topic, then the angle is larger.
Yeah.
That's one way
Okay.
to stack it. So you can see here
Mhm.
in the first one, it's 1 because it's comparing against itself. So it's a complete on itself. The next one is 0.96, so they're very close to each other. But the
Mhm.
other one is negative, it's completely the other way around. So
Mhm.
that's the pillow. It does not
Yes.
compare, it's
Yes.
not the same
Okay.
thing. Yes.
Yeah.
The next one is Euclidean. So
I'm
that one is
grasping.
measuring, yeah, the next one is Euclidean. This one, wait, do you have any questions? Did you want to say something?
No. No, I'm saying that I'm grasping it. Yes. It's good examples.
Try to explain it. If I did a good job, try to explain
Oh, shoot.
what I've done. This is for me. If I did not explain it right, then I need to do a better job.
Okay. Okay, what do you want me to explain?
About the cosine similarity, about how you're measuring two different topics.
Okay. You I to level it or make it not as to not have outliers, which I grasp that because we learned that in stats.
Normalization. Okay, that's normalization.
Normalization, that's what I
Okay.
meant. That's what I meant.
Okay.
Normalization. I didn't get the word. So you find two certain points, so the close, so like -1 or to 1, and then it differentiates like how close or how different they are. So it's like it's a
Okay.
stand pinpoints.
Okay. So we're confusing the two topics here, and
Oh.
maybe I'm going too fast. Normalization. This is called L2 normalization in this specific example. Oh, that's my mom doing the smoothie. The thing. I was like, what is that noise? It's the blender. What is it called? Normalization. When you have these vectors,
Hmm.
in the beginning, before you normalize the vectors, the magnitude, right? The length of the vector, right?
Hmm.
You have a line, right? You can have, I'm going to draw a thing here, like that. And then boom, it does that. So here in this picture, this is without normalization, where you can have a point right here, all the
Yes.
way out there, and this point is right here. That's another topic. Normalization
Mhm.
allows it to do this, to bring it down. Everybody is standardized,
Mhm.
normalized on the same level.
Yes.
That's the kind
I
of the
get
idea
that.
of it.
Yes. Okay.
Now, now after that, we've done that. It's
Hmm.
kind of like pre-processing the data, the vectors. After that, we want to do some measurements. So the vectors that we had, it's in this space, in this space of multiple dimensions, right? I mentioned that 3D. You saw that, right? Imagine you're in 3D. Now you want to see how similar one vector is one topic, like a motorcycle. The next vector captures the meaning of another motorcycle, and then the third vector captures the meaning of the pillow. And
Hmm.
they're all in different points in the space.
Yes.
The cosine similarity measures the angle between these vectors.
Okay. Yes. Okay.
If the angles are closer to each other, they're more
Hmm.
similar in the meaning, in the concept that they're representing.
Yeah.
If it's farther away from each other, then it's less. They're not a match. They're dissimilar to each other. That's base cosine similarity. That's based on angles. That's one way to look to measure similarity using
Okay.
angles, right? The
Yeah.
next
Yeah.
one is called distance. So you have 2 points, and now you measure right here in the red here. You see the red here?
Hmm.
You measure the actual distance between those 2 points like
Okay.
a distance. Like imagine taking a meter, like your body measurement thing you have, and you just
Yes.
measure how far is this point from this point. That's it. There's nothing to do with the angles. Yeah.
Mm.
So you can see here, the measure on itself is 0. There's completely the same. Here, there's a little bit of a difference. It's a different motorcycle, but it's very small. Whereas here in
Mhm.
the pillow, you got 1.5. It's a greater distance from each other.
Mm.
Yes. Okay, cool. Any questions?
No.
No. Okay, great. This is just another type of distance matrix. It's just you see the same thing, 0, a little bit more. Each type of measurements, they're like different tools. It's part of your toolkit. Each one tells a little bit of a different story because of
Mm.
how under the hood the mathematics work. Some
Mm.
tools are more reliable for certain kinds of data than other kinds
Yeah.
of than versus another kind of data. So that's where understanding your data is very key. Is one of your first steps. Is that when you understand the data more, your environment, then you have, let's say, you increase your chances of choosing the right tool to measure these things to make sure that you're going to be hitting higher performances,
Okay.
right?
Yeah, that makes sense.
It's
No,
like
no, yeah.
imagine using a Phillips screw
Hmm.
and a flathead and you have that little cross where you need to tighten it, but you only have a flathead, so you use a flathead. But if you understand that, oh, this thing has an X and I need a screw with an X, then you have a much easier time and you know have higher performance. That's kind of the
Yeah.
analogy.
Okay.
Yes.
I do have a question.
Yes.
Will this be in the exam?
I'm getting very professor now, huh? It's like you see an evolution.
Yeah.
All right, here is visualizing a bigger data set. So I just did three, and I just kind of explained on a very small, just three examples. Now I scale it up to the 30K, the flicker, and I'm using the data set from Hugging Space. So here, this is how it looks up this feature. You get an image, caption, centoids, split, image ID, and the file name. From there, oh, I wonder if the file name is pretty. That could have been a good, handy thing for me to. Sorry, I just got totally distracted right now. I wanted to check something. Here, 1 second. It's not there. Anyways, we're moving on.
Okay.
I'll find that later. Okay, so then I'm showing just a little subset of samples. So like I'm just showing five. There's some people just standing around looking at something. They have there
Mm-hmm.
also the captions. Boom, boom, boom. Also
I see.
captions here. Boom. Same thing, just like the example that we did just earlier. Same thing.
Okay.
Now we're just scaling it up. You know,
Yeah.
we have our little foundations of the bricks. Now we're doing one level higher, scaling it
Higher.
up. Yes. So we extract the images. And so in this case, what we saw earlier, we have five different ways of describing the same thing. Looks like a quite sweaty, smelly dog pile over the rugby ball, but the boys in the blue wanted it more. Two bold men laying on the field, tussling. Rugby players fighting several soccer players, right? So what
Mm.
I did, there was a problem with the BridgeTower that it doesn't like it when I give it. Here is a list of strings. They call these are strings. This whole thing is a
Okay.
string. So I have one, two, three, four, five strings within one list. That's why you see the brackets here, the brackets. So when I put it together earlier, I ran into an obstacle that the BridgeTower does not accept a list of lists because it would put I took out 10,000, right? And I would
Mm-hmm.
have a 10,000, a length of 10,000 list of lists. And inside each element was containing those five strings. But it doesn't like that. It wants a list of strings instead. So then I said it, oh, I'm just going to concatenate those little captions together and just put a space in between those five. And then I will put it a list of strings together. So this is where the whole program is. I concatenated it here. I put it in, and then I started doing a batch of every 20. So I processed 20 images, text pairs at a time. And then that's where I was showing you about, oh, it's going to take 9 minutes, or it's going to take 10 minutes, blah, blah, blah. Remember?
Mm-hmm.
Then I concatenate, and I did the exact same thing again. I normalize, bringing it down, the magnitudes, bringing it down. Sometimes I can have a vector that's way out there. I'm bringing it down, normalizing all the vectors, you know, on the
Okay.
same range. Then here, I'm using a thing called a UMAP. UMAP stands for Uniform Manifold Approximate something, maybe. What does UMAP stand for? I forgot. I know it's uniform. UMAP means, what's the acronym mean? Uniform Manifold Approximation and Projection.
Mm.
So this is a tool that allows you to do dimensionality reduction. So do you know what I mean by that?
No.
Okay. Do you remember when I was mentioning that with
Okay.
the embedding that I
Mm-hmm.
have a very long vector that has many elements,
Yeah.
dimensions,
Mm-hmm. I
right?
know. Yeah.
And we
Okay.
talked about how if you have three vertices, or what's it called? What are those elements? Vectors. Then it
Mm-hmm.
means it's 3D. But right
Okay.
now, with this embedding model, it outputs 1,500 plus or minus vectors. This is a dimension. This is a kind of space that we cannot see. We can only see in 3D, right?
Mhm.
This and then depth, x and y, and depth, x, y, and z. That's how we see it. So I'm
Okay.
using a tool that is able to find all these points in this space, and imagine it's like a sheet of paper. It's like a sheet of paper that is crossing through all the dimensions, right? You have 3D, right? That's how we see 3D. Imagine you have
Mhm.
4, 5, 6, 10. Imagine having a piece of paper like this, being able to cross through all those dimensions and project onto that paper the vertex onto this paper. And then you reduce it to a certain to 3D, and then you can visualize it.
Mm.
There is a loss of information because of that, right? So it's an
Oh.
imperfect tool, but it does the
Mhm.
job to some extent that allows us to make a decision and move forward. So,
Okay.
did you want me to re-explain anything?
No,
It's
that one's just a little, that one's a little bit more.
a little more
Um,
time. Yeah.
yeah. Wait, just explain the like. Let's see. Where? Okay, summarize it even in some in faster terms, I would say. Like, so
Okay.
you,
Imagine this is 2D, right?
yes.
And this thing, the blue,
Mm-hmm.
is the sheet of paper.
Okay.
If I have a vertex here, I project it onto the paper. You see here?
Mm-hmm.
You see those little things, how it's projected, like those little dash lines?
Yeah.
Those the vertex
Mm-hmm.
are projected onto a sheet of paper. And you saw how that thing right there, that
Yeah.
thing is what? It's one dimension. It's only a
Mm-hmm.
line. A line is one dimension.
Mm-hmm.
That's from 2D to 1D. You get it?
Yes, I do. I do. That part
Yeah.
I did. Yeah.
So you project. It's like a projector
Okay.
onto, right? You have an image, you project it onto a 2D space,
Great. Yeah.
right? And imagine the projector, that's in 3D because you have this, but then the projector is not on the wall, it's away from the wall. So
Mm-hmm.
that is like a vertex projecting onto a flat space,
Yes.
right? So it's
Mm-hmm.
reducing dimensions. It's
In the
reducing from
information.
3D to a 2D image that you can watch.
Okay.
That's the
Okay.
idea.
Mm-hmm.
So then I did some k-means clustering, and this is what I resulted here. It's this is from a dimensions of 1,500. You get this this thing. Not always perfect. I guarantee you, if you run this again, it will be a different kind of thing because there's some randomness to it on how it creates these things. But if you look in
Mm-hmm.
this way, you see some vertices here. One, two, three, 4. There's like these little clusters here. Unfortunately, the k-means is not doing the greatest job in this sense because the k-means is supposed to, you can probably see the different colors, right? You see yellow and purple.
Mm-hmm.
Yeah, the k-means doesn't do so well when you have data that is like in a very weird shape like this. So in order for me to do a better clustering to say like this is all one color, like this little arm here, I would need to use a different tool that is able to account for very irregular shapes. So in this sense, this is an example of using the wrong tool for this specific data. That's why data understanding is very important.
Mm-hmm.
t-sne is the same thing. It's the same thing of reducing dimensions, but it does it in a different way. And so it doesn't perform as well here though. So UMAP performed better in this case. I could maybe do some tuning here on the perplexity, and it will create different shapes, and then maybe something useful will come out. But in this case, nothing is really useful that I can see here. I cannot
Yeah.
make a decision from this. So that was my thing. Yeah.
Little big claps, big claps.
See?
That was I learned a lot.
Yeah.
Maybe I should start coding.
There you go. I think we're about to die here though on the.
Yeah, maybe. I think. Oh, we have 6 minutes.
Oh, we still have 6 minutes.
Wow.
So,
No,
did
it
you?
was yeah. I'm quite